So hearty welcome for everybody. In the next 20 minutes, I want to explain you our concept of trainings, especially for our partner in India. And I will do this by explaining a little bit the methodology and our approach, how to perform such a training for you. At the very beginning, of course, you should know there are two types of FMEA. That could be the Design-FMEA, and that symbol, that picture, is, of course, is a picture for design. That's a whole vehicle. And on the other end, we are also busy to learn how to perform a Process-FMEA. These are the two aspects for a FMEA training. Some companies are responsible for both. They are responsible for the design of a system. Then, of course, they have to perform a Design-FMEA. And very often the same company is also responsible for the operations in order to manufacture it. And they are also responsible for the Process-FMEA. The way how to perform a FMEA is defined by technical standards. The most powerful technical standard is coming from automotive industry, from AIAG and VDA. You know, AIAG, that's the American organization for car manufacturers, and VDA is a German organization for car manufacturers. And they are very busy together to create a common standard how to perform FMEA. And around about 2 years before, they published a US/German standard to describe the methodology. And this is really the core element of our training, because it's more or less a global standard. We do not have a FMEA standard in China or in France or in Italy or in India. So it's more or less a global standard. So in the next minute, I want to explain the 7 steps. And I want to explain how we will perform this training. So step 1 is planning and preparation. That sounds pretty logical, of course. Every aspect must be planned, must be organized, of course. But if we are busy with Design-FMEA, we have to perform boundary diagrams. That's a type of block diagrams. And this is really the very first aspect for our training and qualification, how to perform block diagrams in order to prepare a Design-FMEA. And here is a pretty nice and simple example. That's a wireless mouse. And at the very beginning, we have to define what is in, what is part of the system. That could be a battery system, a plug system, a PCBA, etc. That's inside. Then we have to identify the interfaces. There is the interface number 1 between the wireless mouse and the computer system, etc. At the end, we will identify a lot of interfaces, and we have to, let me say, we have to categorize these interfaces. And at the very beginning, there are 3 types of categories for interfaces. We can transmit signals, we can exchange energy, and or we can exchange material. So this is step 1 in order to prepare a Design-FMEA. Later, we will skip to the Process-FMEA. Therefore, you will not find a boundary diagram for processes. That's another approach. But also in the Process-FMEA, step 1 is planning and preparation. That's it. Let's skip to step 2. Step 2 is the structure analysis of a system. So we have to understand, especially for machines, that's really complicated. There are a lot of levels. On the top level, we will see the whole system, the whole machine. And then we will see subsystems and systems and assemblies. At the end, we will see single components. It's a little bit like the bill of material, a visualization of it, of course, but it's really tricky. In the training, you will understand that you have to use the terms coming from the bill of material, but the boundaries are totally different. For example, we have a heating system inside or a cooling system, and such systems does not follow exactly the bill of material. We have to learn how to think in systems by using components. Where's the boundary of such a system? And we will also discuss it, how to perform such structure analysis for software scopes. Totally different. This is also an aspect of our training, to get a deep understanding how to perform a structure analysis for such very different objects. Some objects are really simple because you can follow totally the bill of material. The boundaries are totally clear, but not for all. And let me say, mechatronic systems, mechanical systems with electronic and software, definitely it's a little bit complicated. So the structure analysis for the Design-FMEA. So at that picture, it looks pretty simple and pretty logical, I think. One more aspect, very often, especially in your industry, you will not design everything by yourself. You will be in the role of a system integrator. And this is also an aspect of that business, to identify the black box system. That means which system will be integrated. And at the end, it is a black box for our design. And you will learn rules how to handle also black box systems. This is step 2. Let's go to step 3, the function analysis. So we are using the structure tree and we have to add the functions. What is the function of the mouse? What is the function of the mouse system? What is the function of the computer system? What is the function of the battery modules, etc. So at the end, we will see single components. And we have to link these functions in functional webs. This is, let me say, the most efficient way to drill deep into technical systems. Everybody can feel there's an interaction between functions on different levels. So for example, this pretty nice example of a wireless mouse. So what is a function of a wireless mouse? Convert movement into signals. That's also very tricky, because most of the people will say, okay, what is a function to move the cursor, etc. This is wrong, or this is a function on the wrong level. In the technical way, we have to understand what is the input, what is the output, and then we have to find the right wordings for the functions. The input is movement, the output are signals. What is a function to convert movement into signals? What is the function of the housing assembly to hold the PCB in place? And now you can feel there is an interaction with how and why. So if we start here and we go upside to the top level, to the vehicle level or computer level, the question all the time is why? Why do we need the functions to hold the PCB in place? And we will find the answer one level upper, to convert movement into signals. Why do we need this functionality to transfer signals to the computer? Why do we need this functionality to transfer signals to the computer? You can't read it here. To control the computer by a wireless mouse. If we drill down from the top level, the question is how? How can we take care that the functionality to transfer signals to the computer will work? We do need a mouse to convert signals, movement into signals. How can we realize that? Therefore, we do need a housing assembly for the fixation of the PCB. And the very last level, also how, we have to understand which product characteristics of the lower body is needed, specified in the right way to hold the PCB in place. These are the geometry of the lower body and the material properties. So we get a lot of functional webs to create a deep understanding of the system. And the next job is pretty simple. Step 4 is the failure analysis, and the failure analysis is not critical. It's really easy. The challenge is the function analysis. So we have to convert all the good ones into the bad ones. Does not hold the PCB in place. the wrong specification of the geometry, does not convert movement into signals, does not transfer signals to the computer. We did it, of course. Here we are, based on the function analysis. And now it's really cool because the position in the structure tree defines you are the cause. If we specified the fixation features wrong, this is a cause. Next level, that's a failure mode. PCB locating, not maintained as intended, that's a failure mode. That's the effect. The movement, not convert into signals, and that's the effect of the effect. Signals not transferred to the computer system, and the effect of the effect of the effect, we are not able to control the computer by the wireless mouse. That's a failure web. And especially in your industry sector, you will see more than 3 levels, of course. And that's the only way to handle such an aspect. If we have only 3 levels, we have a cause, a failure mode, and an effect. But in reality, in mechanical engineering, most of the systems has 4 or 5 or 6 levels. That's the only way to handle that. I think it's easy to understand. So in the next step, we have to perform the risk analysis. In the training, you get the right ideas regarding how to mitigate risks. We do have 2 variables. Variable 1 are preventive controls, how to generate preventive controls. And the second one is, these are detection actions. To be honest, these are verification and validation activities. In order to provide evidence that the design is robust, we have to list these verification and validation activities. And then we have to decide how safe we are with these preventive control and these detection controls. And the results create the occurrence number. So the occurrence number is the quality rating of the preventive control. If the preventive control is really capable, the occurrence number is low. That means the likelihood that we will see such a trouble is very low, and the risk is very low. Same question for the verification and validation activity, how safe we are with these type of verification and validation. And on the other hand, how representative are the samples? Is our sample really representative for the next 10 years? That will be summarized, and you will learn a lot of catalog how to do it in the right way. Is summarized in the detection number. If we link these with the severity number, so severity number is linked with the effects on the top level, we get a good overview regarding the risks. That's step 5. And of course, we have to specify responsibilities for the actions and deadlines. If the risk is too high, we have to skip to the next step, step 6, optimization by additional controls. And we need additional preventive and or additional detection controls with responsibilities. In former times, the severity number multiplied with the occurrence number multiplied with the detection number. That's not state of the art anymore. Based on AIAG and VDA, we do have action priorities. That means a combination of severity, occurrence, and detection automatically bring you in the category high action priority, medium, or low. And that's the information for the top management. Of course, the top management is interested to see and to understand what are our highest action priorities based on these FMEA. Do we have to invest more in preventive and or detection controls? That's automatically step 6, of course. And the very last step is 7. That's the documentation for the stakeholders, especially the documentation for the top management and the customers and the auditors, you will learn a lot of things, how to create a good overview regarding the risk, not by reading the whole FMEA, not by reading hundreds of pages of FMEA. The top management will not accept it, so we have to summarize it in a top management information. So these are the 7 steps coming from for the design FMEA. And very shortly, let me skip to the process FMEA. You know, the names are the same, of course, but the content is totally different. Give me a second to use our small notebook. And of course, you will get a lot of good documentation for that. So step 1, of course, you know, planning and preparation. No boundary. We will see a flowchart with the value added operations like drying, molding, cutting, and a lot of other things. This is the aspect of how to plan and how to prepare a FMEA based on such a flowchart, of course. Of course, you know, step 2 is the structure analysis. In the process FMEA, we do have only 3 levels. That's pretty nice. Level 2 is the flowchart. Level 1 is the name of the whole process. For example, the mouse housing manufacturing. Level 2, the flowchart. Level 3 are the needed resources divided into the 4M: man, machine, material, and milieu. On the other hand, don't write man, write operator or maintenance mechanic, write inspector, quality inspector. Don't write machine, write injection molding machine, injection mold, end of arm tools, inspection gauge. Material, don't write material. Material is plastic pellets. Maybe it's compressed air, electrical power, what is needed coming from this category. And last but not least, the working conditions. That's the surroundings like temperature, humidity, etc. So that's the structure analysis of a process. Only 3 levels. Everything is much more easier. And you will learn in that training a lot of rule how to perform it in the right way. So for example, very often the people said, okay, let me see, maintenance is also part of our flowchart or qualification of our people. And this is really wrong because it's needed for the FMEA, but it's a control. It should be not part of the flowchart, and it's not an objective to perform analysis. It's content of the FMEA. It's really tricky. So function analysis. So we have to document what is the function of the operator. Of course, one function is sets operating parameters. What is the function of the injection molding machine? Mostly we handle it in functions and additional by process parameters like the injection pressure or the barrel temperature or the cycle time and all the other ones. What is the function of the molding? To transform plastic material into a finished form. You will learn to make it much more specific, to create a list of product characteristics, all dimensions, surface roughnesses, etc. Level 1, what are the function of the whole process with all these operations at the end to meet the cascaded design specification, very generic, of course, and to meet the economic targets. This is one functional web. At the end, we will create such functional webs for each product characteristics in level 2, like thickness, surface roughness, color, and all dimensions. And how and why works pretty in the same way. Next step is easy. We call the next step Mr. Murphy step. Everything what can go wrong will go wrong. That means the operator sets wrong operating parameters. The injection pressure is not, there is no process capability. The barrel temperature is too high or too low. All these level 3 stuff are potential causes. We will not realize the right dimension as a failure mode and the effect. We will not meet the design specifications, and we will not meet the economic targets based on scrap and rework. And here we are, here it is. So that's pretty nice. Level 3 is the cost level. Level 2 is the failure mode level. Level 1 is the effect level. That's it. Let's skip to step 4, the failure analysis. We have to add controls. Give me a second. Here we are, step 5, sorry. We have to add preventive controls. You will learn that the preventive control is focusing on the cause. The detection control is focusing on the failure mode. So we will learn a lot of rules, how to perform it in the right way. And of course, once again, the occurrence number is the quality rating of the preventive control, and the detection number is the quality rating of the detection control. So by this way, we will create a good overview regarding the hotspots, regarding where are the most risky aspects in our process. And then maybe we have to skip to step 6, optimization by additional controls. And the preventive controls and detection controls are totally different. You can't use the same coming from the Design-FMEA. And at the end, we have to let me say, document the results. We have to create a good overview regarding the existing risks for customers, top management, auditors, internal auditors, external auditors, etc. So that was in a very, very short way, the first overview regarding the 7 steps. And for all of these steps, we will define a lot of best practice and examples and catalogs.